So I'm asking, what is the general solution to an equals negative 3 times an minus 1 plus 2 to the n minus 1 for n at least 1. So notice I haven't given you an initial condition here, right? I didn't say that, normally I would say this holds for n at least, or, often I would say this holds for n at least 1 and a0 equals something, right? But here I'm just asking for the kind of general solution for this recurrence. So basically at the end, we're going to have a0 is going to be an unknown, okay? And that's the way you want to, so when I ask you for a general solution, you want to leave it in a form where you have some unknowns. Just to kind of connect this back to terminology we introduced last time. So this is first of all, it's a linear recurrence of order 1, linear recurrence relation of order 1, because it's an is just something times an minus 1 plus a function that depends on n. And when this function, so if I had a 0 here, right, if there wasn't anything here, it would be homogeneous. But since I have a function of n here, which is not 0, we call this non-homogeneous. Okay, let's try to solve this. And I'm going to solve it using kind of the main trick that I told you about last time, which is this kind of telescoping trick. So this gives you a kind of nice way, I think, to kind of algebraically work out the solution to a first order recurrence relation. So do people remember how this worked? So we're going to start by just writing out the recurrence for an, right? And so you'll see how the algebra works later. It's going to be kind of, I think, convenient. It doesn't really make a difference either way, but for kind of having a systematic way of doing this, it's useful to just write all the stuff involving the sequence on one side. So an plus 3 an minus 1 equals 2 to the n minus 1. So I just moved the 3. So this was our original equation. I just moved the 3 an minus 1 to the other side. And then you can write a similar equation involving, so here we had an and an minus 1. And you can write a similar equation involving an minus 1 and an minus 2, an minus 2 and an minus 3, and so on and so forth. So basically here the value of n is going down by 1 each time. So on the right side, I've got 2 to the n minus 1, 2 to the n minus 2, and so on. Okay, so the kth, so the equation involving an minus k is like a sub n minus k plus, the term that comes below it. So there's 3 times a n minus k minus 1, and then you have this on this side. Okay, and we want things to cancel, but obviously if you look at this, what I want to do at some point is just add up the left-hand side, add up the right-hand side, and just hope that a whole bunch of stuff cancels. But obviously if you look at this, you can see that if I add these, then these things don't cancel, right? If I take 3 of an minus 1 and I add another one, it's just going to give me 4. And I wish that they canceled. So what should I do to the second equation in order to make these two things cancel? Any thoughts on that? Oh, we've got some answers here. Right. So there's two things that seem natural here. One is to multiply by 3 and one is to multiply by negative 3. In this case, it turns out negative 3 is the right thing to do. If I was subtracting, then I guess I could do it by positive 3 and subtract it, but subtracting is confusing. Let's just add. So we determine what we need to multiply the second equation by in order to cancel it, and it's minus 3. And then we could think about, okay, suppose I multiply this equation by minus 3, and remember, so this is something to not forget. You have to do it on both sides, right? Otherwise, you break the equation. But then you could think, what do I need to multiply the next equation by? Because here, so I want to now cancel this one with that one. Something like that. So don't forget the minus signs though, because, so here, if I multiply this out, I'll get on this line, I get a minus 9 an minus 2, right? So in order to cancel it, I need a 9 an minus 2 here. Exactly, yeah. So I'm glad that at some point I was going to do this example with just a 3 here instead of a minus 3. I'm glad I did the minus 3 because I think, people might have if you encounter this on your homework and I haven't done an example, you might have been confused. But yeah, so here what you want to do is multiply it by 9, which is minus 3 squared. Because yeah, then on this line you get a minus 9 minus 2. Here you get a plus 9 minus 2. And when you add them, those things are going to cancel out. And then hopefully you can kind of see the pattern. So on the first line I multiply by nothing. The second line I multiply by negative 3. Then negative 3 squared, negative 3 cubed, so on and so forth. So this line here, like the line involving an minus k gets multiplied by negative 3 to the n minus k, right? And if you think about what happens when you add up both sides, then practically everything cancels on the left side, which is like something we're very happy about. Because and actually even more, what makes us even more happy is that the an doesn't cancel. Probably, yes. Thank you. Sorry for the typo. Yes, so this n minus k here, I wish I could say that I put that in there to see if you're paying attention, right? To see if anyone can catch it. But actually that was just my mistake. I guess I was doing this too quickly. But yes, so thank you for that. So that's a k. Yeah. So, okay. So if you add this all up, you have that this one doesn't cancel. All the intermediate ones cancel. So including like a1 down here. But then this one doesn't cancel. And you have to remember so I need to kind of multiply this in to that one, right? So what you end up with is an plus 3 times negative 3 to the n minus 1, a0, equals this sum on the right side. So it's good that I've got this fixed because actually it matches what I've had here, right? So is it clear how we get this? So this is, at this point, we've basically solved it. The only thing is that it might be nice to get this, instead of having a sum here, to get this in terms of just a function of n, right? It'd be nicer to have that than have to compute this sum. Okay, so what is this thing? Now, because we haven't done very many of these examples yet, this might look like something we can't do. But actually, in disguise, this is something we already know how to compute. Okay, and this is kind of bringing things back to how the generating functions worked and all that. So we can actually we can compute this. So what I would suggest to do here, so I mean this looks weird because we have an n here, n minus 1 here. We've got this negative k, we've got a k, but actually it's not that complicated. So if you just take out the 2 to the n minus 1, you just take it out in front, and then you just realize what is a negative exponent? Well, it's just 2 to the minus k. The way negative exponents work, that's just a half to the k. So I can just replace that by 1/2 to the k. I can kind of put everything together, and I just get negative 3 over 2 to the k, and I'm adding that from k equals 0 up to n minus 1. And this is kind of like a lot of these sums we saw in generating functions. Like if you think of this as being x, then this is like the sum k equals 0 to n minus 1 of x to the k. So can anyone tell me what an expression is for that? So yeah, here just treating x as a variable. So I want to say that this is equal to something which has a nice closed form. So maybe we don't remember this. So okay, what if I was adding up to infinity? Yeah, if I was adding up to infinity, I'd have 1 over 1 minus x. But I don't want to add to infinity, so I want to subtract. So if I was doing, so that's going to end up being right. So to do it kind of step by step, right, I can take 1 over 1 minus x, so that's the sum that goes to infinity. And then I can so if I do this, so if I take x to the n over 1 minus x, so that's the same as taking the sum from k equals n to infinity, because if I take x to the n, so maybe so this is a kind of side calculation, right? But x to the n over 1 minus x is the same as, x to the n times the sum k equals 0 to infinity x to the k, which is then just the sum k equals 0 to infinity x to the k plus n, right? And then if you think about this, like the first term is x to the n, then x to the n plus 1, etc. So this is actually the sum k equals, so sorry this is getting a bit messy, but k equals n to infinity x to the k. Right, so this is our expression, which if you do, so as was suggested in the chat, if you do a little bit of simplifying, So you can put these together because they have the same denominator. You can multiply the top and bottom by -1. And it gives you a kind of nicer looking formula. So I know that, yeah, you guys are still, I think, working on assignment 4. You're getting hopefully some practice with doing these things, but you need to, yeah, this needs to be something you can do. So computing this or getting an expression for this is something you have to be able to do fairly quickly. Okay, so we can do that. Yeah, so this is just what was written before on the previous slide. So therefore, okay, and this is yeah, like was said. So this is x to the n minus 1 over 1. X minus 1. So now I just plug in my -3/2 here. I get -3/2 to the n minus 1 over -3/2 minus 1. At this point, if you're doing a test or something, you can just write this down. Meaning, okay, so this is only part of our previous answer, but I'm going to do a little bit more algebra to make it look nicer. You don't really necessarily have to do that. But yeah, if I want to do a little bit more stuff, I can say the bottom is -5/2. So this is -5, and then I can take a 2 on the top, right? -5/2 here. The way fractions work is it's, like this. But yeah, none of this is necessarily something you have to do. Okay, and if I plug that in to what I had before, so what we had was this formula that this is -3 to the n a0 plus 2. So it was 2 to the n minus 1 times our sum that we had before. At the end of the day, the final answer looks like this. But like I said, you could have left it, if you leave your final answer like this is a perfectly acceptable final answer.